Production and Automation and Robotics in Shipyard. And this class, the lecture material is prepared by Professor Kim Jae-hoon. He was in Samsung Heavy Industry for a long time. He covered this material 2 years ago, but this time we will cover, myself and Bart will cover this. Right? Offshore and shipbuilding industry, especially the oil and gas, and that is so. We already covered this one, but we will review this. And then exploration needs drilling too. But anyway, exploration can be done by, say, sonar system. We already see in another lecture. Also, they need drilling for sure, make sure. And then go on to production. If the drilling is successful, there is many possibilities. And then we need the transportation. So for the shipbuilding company, shipbuilding industry, drilling is the first place they can involved to make drill ships and semi-rig and jackups for drilling. For the production, they build FPSO. FPSO is a short name of floating production, storage, and offloading. Okay? And TLP type or platform type is a type of them, tension leg platform or something. And in transportation stage is very traditional. You need LNG carrier or crude oil carrier. Okay? So LNGC is a liquefied natural gas carrier, or VLCC is a very large crude oil carrier. Also, recently we trying to cover the Arctic Ocean because there are remaining oil and gas reservoirs. Now they are saying these two, including offshore industry. This is a traditional shipbuilding industry. Shipbuilding division, offshore or ocean plant division is different. They are separate out inside the shipbuilding company. Shipbuilding industry too. Okay. And this is a mega structure of the world. This is a new tallest building in Korea, just opened in Seoul area. So it is about 100 floors. Just before then, up to last year, oh sorry, this is Korean. 63 is the number of floors. The building name is same. That was the tallest one in Korea. But Petronas in where is it? Malaysia, right? Taipei, and Khalifa in Middle East. Those are tall buildings. Whereas the ships are container ships and FPSO, LNG FPSO. It's big, right? So comparable to largest building or tallest building in let's see also. So bulk carrier also big. In shipbuilding is made of blocks, so we can say block building. That is developed the block construction. The technology is developed mainly by Japan. They exercise the block construction, and because of the welding technology that is developed during the World War II. And then shipbuilding process, they start from smaller blocks to larger blocks. And PE means a pre-erection. Pre-erection. Erection is here. Pre-erection block is aggregation of unit small blocks into bigger blocks. And then erection is coming. And then launching in dry docks. So this is Lego toy, but we can see that how ships are built in blocks. And this is very big one, big block, or super ring block sometimes they call it this. And this is more detailed production process. Unloading of steel plate coming from steel making company. In Korea, POSCO is a steel making company. They brought in steel plate. And then priming is small, primary painting for rusting, to prevent rusting. And then cutting of pieces, something like angle here. Right? And then the cutted plates are assembled into, starting point can be sub-assembly, and then a little bit more into an assembly line. So they call this is lines of places inside the shipbuilding company. So sub-assembly line, cutting line, assembly line. If you have a chance to visit large shipbuilding company, you can see that divisions and lines. And then grand assembly, big assembly, right? Big assembly. In Korean, develop 공장. There is a special plant or housing for a big assembly blocks. And then that goes outside. Oh, there is some division maybe inside here. So inside or outside. Let me show this one. So indoor, outdoor. So block, and then up to now is a steel plate and for structural assembly. And then they started to putting outfitting. Outfitting means pipe and cables and other things. You can think about this building. When they build this building, they started with the building of the main construction, main structural body of, say, concrete and steel construction, the main body. And then they started to put some pipes and air conditioning lines and cables for electricity, other things. We call these additional things as outfitting. Okay. Additional, that may be not proper word. So we can divide into two parts, structural part and outfitting part. Money may be, cost may be higher for outfitting, but the shaping is mainly coming from structural part. So up to here you can say structural building, and then outfitting goes on, even though they cost higher. And then painting, it is final painting. Not maybe final, but almost final. This is primary painting only for prevent rust. And then goes outside. This is inside the housing. And pre-erection, and then erection. Pre-erection is some more assembly, bigger assembly, big block. Because of this is possible because of the larger cranes capacity. If you don't have any big crane capacity, you cannot do this one before. Nowadays, Korean shipbuilders has a big gantry crane. Also, they also use floating cranes, much bigger. So that the block size is becoming bigger. So when I was young, there was no such a process as a pre-erection stage. But this is a new stage, new process, because of the bigger cranes. And then erection goes into dry dock. Right? And then launching, because of the water is incoming, so it's floating. And after that, also the outfitting goes on. But I can say that this main engine is erected or assembled inside dry dock because it's a big item, and also they should be located bottom side of the ship. So they need a big opening when the engine is coming. So the main engine is assembled in this, but still they need more fittings, something as a cabling and piping and control. Especially the control devices, sensing devices should be put in the main engine. And then sea trial, this is acceptance test, something like that. The owner, the contract side, they should check whether the main contract items such as speed and tonnage or cargo capacity is matched. That is final check before delivery. This is just a ceremony. Question? Right, you can see one video. Let me see. This is a mega ship, mega float crane, and this is coming from Samsung Heavy. Sound. This is a cutting and also sub-assembly line. This is super ring blocks that is carried by Goliath crane. But still it is dry dock, so they need land-based cranes. But this is floating crane. $3,600 ton. But now Samsung has 8,000 ton cranes. And also Hyundai built 10,000 ton crane recently, 1 year ago. It's a floating dock. They divide a ship into 6 pieces, right? Only 6 pieces. A launching. There's cutting process. That's the raw material, the plate coming from steel company, and cutting is going on. into pieces. And bending on cutting. This must be bending. Simple bending, right? Rolling. And sub-assembly. Welding robots. Because of the structure is complicated, robot is not easy to run over. Thruster, that is a thruster. There's a fitting for block lifting. The wind is blowing, then block is moving, so they cannot work. And also wave, the area is protected area, so wave is not a big problem. Sometimes it works. You need to have a smallest gap, right? The requirement is 2 millimeter. The gap requirement. But you should think about how to assemble them in the factory to make them precision fitting. Right? Not only transportation, construction in pre-erection should be done precise. This is 8,000 ton crane. Okay. Okay, question? No, then we go on to. So this is a block division. This is an old slide, but you can say this. Now you can say this is a pre-erection size something. Right? So that is approximately the size of 20 meter. That is a standard for shipbuilding company, but that is because of the size of the indoor factory. There is also crane inside the indoor factory, so there is a limitation. Probably the most important limitation is transportation. Transportation by crane, transportation by special trucks. I cannot remember the correct name, but there is a flatbed, big trucks, they transport blocks, right? That gives you size limitation. Nowadays, as I say, they trying to make bigger cranes because they want to make smaller number of blocks, big blocks. Why? Because to increase the production per day or per year, per month. That they are saying productivity of the shipbuilding company or shipyard productivity. Their target duration inside dry dock is now 1 month. It was more, say 5 months before. Nowadays, I say 2 months, around 2 months per ship, per thing. So if you reduce the stay duration inside the dry dock from 2 months to 1 month, you can say that productivity of the shipyard is increased twice, roughly. Right? That's why they want to make bigger blocks to reduce time inside dry dock or crane. So this is very small size scales pieces, and they start from a small typical steel plate about say 2 centimeter thickness or 1 centimeter thickness or 2 centimeter. 2 centimeter is around here, right? Thickness of the plate, and then cutting and welding and welding and bending. Right? So this is coming from a drawing or design, right? And then you find out unit block, or say this is sub-assembly, you can say. And this is coming, the flow chart. Flow is coming from here. Right? So starting from the plate. Right? Oh, there is more. They call this cutting from plate, and then welding, cutting, forming, sub-assembly, panel line, sub-assembly line, assembly line, in flow. And grand assembly, right? And pre-erection, maybe so this grand assembly say is a block, a portion over here, right? So that they need to have a pre-erection and coming more assemblies. And same picture as before. So it's an indoor and outdoor production process again. So nowadays the crane gives you super blocks, bigger size. The Goliath crane, the limitation of capacity is now around 1,000 ton, less than 1,000 ton. Biggest inside Korea. The land-based Goliath crane is 1,000 ton. So that you need to have a smaller, lighter weight, right, than 1,000 ton. So you can imagine the size. But it goes into floating crane, you say they start from 3,000 ton, 5,000 ton, now 8,000 and 10,000 even. So it's 10 times bigger than land-based crane. No? So then you can see that how big the block can be. All right? No more. No question. And go on to Bart.
All right, I will continue this lecture about production automation and robotics in the shipyard. Here you see a pie chart of the man hours made of building a very large crude carrier, which is a very big ship. As you can see, the majority is made out of the welding, painting, and the fitting part, which are relatively simple tasks. I mean, 800 kilometers of welding, which is mostly straight lines, making straight lines. Painting, almost 500,000 liters of paint, adding to the ship, which is not really a job where the creativity of humans is needed. Same for fitting. So if you look at the priorities of research and analysis in shipyards, it comes down to welding, the painting, and the outfitting work. You want to be automated or replaced by robots. Yeah, then you start easy, or the easiest. First semi-automation and then the full automation. And you start indoor rather than outdoor, because indoor climate is easier to control, of course. Before you start that, you have to consider the characteristics of the research and of the offshore and shipbuilding. Ships are large, complex structures. Speaks for itself, I think. They have to survive and be active in a harsh environment. I mean, it's out on the sea. They're made in small quantities. It's not like you're building a mobile phone which ships off in millions of the same unit. There are a few same ship model if you're lucky, but that's it. And the conditions in which the ship has to be active are changing. So that leads to a few main focus points in the research and analysis. Well, safety, which is pretty obvious, I think. One of the most important focuses of offshore and shipbuilding is safety, so which is also the case in the research and analysis. Mobility. You have to imagine that the ship is very big, of course, and if you have a static robot which cannot move, it's not very useful for a big ship. You cannot move the ship around the robot, so the robot has to be mobile. Also small and light. I mean, if you build a very big robot which you cannot lift easily, well, it's not of much use as well. Reliability. Of course, the robot should produce the work at least as reliable as the way humans produce it. Yeah, also pretty obvious. Robustness. Well, it counts for the quality of the work the robot should produce as the robot itself. I mean, the ship won't break if the robot, touches it or whatever. So the robot itself also should be robust. And intelligence, as the ship changes. I mean, you build a few ships of the same model, and then you go on to the new model. You shouldn't need a new robot model for each new ship you're building. So it should have some intelligence to adjust to the new ship you're building. Which come down to a few fundamentals. Structure. I'm not really sure why that one is there, but it should build a structure, I guess. I don't know. But the other three are logical. You have the control. You should be able to control the robot, tell him what he has to do. Sensors. It should be able to know its environment and be aware of its environment. And the ship, because of he has to do different tasks every time. And software, which is sort of the brains of the robot. Which comes down to the SI intelligence, which I assumed was swarm intelligence. Not sure if that's true. Professor? Is that swarm intelligence? SI?
System integration.
System, oh, okay. Well, then it's good that I didn't add a video about swarm intelligence. System intelligence. Integration. Okay, I'm sorry. Then I have nothing to tell about it. It should be all integrated in the robot, I guess. Yeah, here's the same picture again. As mentioned earlier, the start of the automation and robotics should be indoor rather than outdoor. So that's above the red line. I couldn't find any videos or something about the labeling and cutting of profiles, but I think the labeling and cutting of profiles is pretty straightforward. You have in the shipbuilding process you have a lot of hundreds of thousands of parts, and if you cut them, you have to label them in order to not lose them or forget what they're about. There are hundreds of thousands of them, of parts, so if that could be done automatically, it spares a lot of time, but I think it speaks for itself what it does. Yeah, there's a video about the automatic welding at the shipyard. I'm going to show you this first. I mean, you can all read what it says. I don't know how to put the volume up. But he says he's going to visit the robot, and he's making a very bad joke about that man being the robot. It's not that funny. The man says, no, I'm not the robot. But it all comes down to he's the operator of the robot. And what are you doing then? And then he will explain what he does. He has a scanner there, the sensors. He scans or makes a picture of the metal plate beneath him. This is the software where you can adjust some parameters, and then you can control the robot and can start the welding process. Yeah, of course I'm very dedicated to giving you a perfect lecture, so I took a field trip to the DSMB Shipyard, especially for you, of course, to take a closer look at the first steps of the shipbuilding. This is the part where they do the welding from the big flat pieces of metal to the first stages of a block. That's me. Those behind me are the pre-erection blocks, I guess. Yeah, here's where they put together the first big pieces of very large pieces of steel, which are not large enough, obviously. They first spot weld them together to fix them in place with the large arms over there. And then, as you can see, they make the weld strong. You can see the weird endings of the weld. They do that because the ending has, if you stop at the end of the plate, you always have some sort of weird gap. And now the weld goes straight, and they later cut off the end of the piece. And this is sort of a bad picture, but the weld is true and true. It's not a weak spot. They say it's even stronger than the rest of the metal. Yeah, this is the lower part of the metal, and it's the weld is as thick or even thicker, as you can see, as the rest of the metal. After they put together the pieces, they place the beams, which is also done by first spot welding the beams on the metal plate, and after that the arms make it a smooth, long well. And that's until the part where they adjust the beams is one long production, how do you say that, road, which just continues to roll. I forgot what the production is per day, but it's pretty huge, and they have a few of those streets. And when it's there, it can continue in different directions in the factory. For example, straight through, where they build walls and sections on top of it. This is a zoomed in picture of a welding robot, which the biggest part of the welding robot which is this and this, is actually the welding material, because they want to keep that close to the robot. And the welding thing itself is pretty small. And here you can see above are hanging all the welding robots. They can put them down, and the welding robots can scan their environment, placed in a space like this. They know where they are, and they start welding. You put them up, and you place them in the next hole. And that's all pretty easy for robots, straightforward. Until the moment you have curved parts, like the one there. Then it's starting to get a bit harder. For example, the placing of a huge piece of metal that is curved alone is quite hard. All the beams beneath the piece of metal had to be adjusted by hand before they could place the piece of metal on top of it.
They call it the jig.
Jig?
J-I-G.
Jig. Okay. But it's this still is pretty man-hour intensive, I guess. This welding part, and most of the welding here was still done by hand. So apparently the robots are not that advanced that they can know all the curves they have to make. So only the simple welds can be made by robots. I don't know if it's everywhere, but that was the case here. Yeah, the block painting. Painting was the second largest man-hour intensive job. Yeah, grit blasting. I think that's the cleaning of the metal. I mean, a big block often stays outside for quite a while and gets a bit of rust and has to be cleaned. Grit recovery. Then you have to spray it. The pieces where they are melted together later, they cannot be painted, so they leave about 5 centimeters of metal unpainted. And then the drying part. The videos I found all were still they were still manually painted, so I'm not sure if there is a fancy robot to do the painting. But I mean, 500,000 liters of paint, it should be way better to do that by robotics. But the surface is so big that it's quite hard to design a robot for this, I guess. And then the LNG tank, which is a pretty big tank. You don't really see it of this picture, but I got a video of the size of the tank. Yeah, I'll show you that first.
LNG 생산 기지의 저장 탱크에 이미 한국형 멤브레인 소재 기술이 이용되고 있다.
I have no idea what to say. It's just about the picture to get an impression of the size.
LNG 선에도 우리 기술이 발전될 전망이다.
Yeah, as you could see, it was really big, and it consists of a lot of these beams coming together.
They are saying this is left hand side is a GTT, is a company from France. They have a patent for membrane type LNG tank. The right hand side they are trying to develop Korean version of membrane.
Yeah, the only pictures I could find of the LNG tank were D's type. So I guess that company is doing pretty well so far, but maybe the Korean patent can change that. Yeah, they used the so-called spider robot or delta robot. I assume that was the same. You can get an impression by how flexible this robot is. Because inside the tank a lot of welding has to be done. It's also shown by this picture. And if you have to do that all by hand, it's going to take a long time. So if you have robots who can flexibly adjust to all the squares, and it should be better. Yeah, so that was the welding, painting, a sort of fitting, as this is. And that was the presentation. Any questions or suggestions?
When did you visit DSMB?
That was over a month ago.
Months ago.
I didn't know my subject yet, but I made pictures which were applicable to the subject.
Hello. I bring two topics for this class discussion. The first one is how does the UUV, the unmanned underwater vehicle, decide its velocity, which method would be used for navigating. I want to talk about that. Which method would be used to check its velocity itself, like the case for the boat. They uses the Doppler logger, like send the ultrasonic under the water, so that they use the Doppler frequency. They measure the Doppler frequency so that they can measure so that they can measure its velocity, like that. Yes. I bring very fashion ones and the new ones, not the new ones, but ordinary ones. So you are not. You can suggest very easy one, I think. You can. This first one is sonar, equipped sonar. I
don't know anything about this.
For example, the one more thing, like throwing some material and detecting the material's relative position, so that it can measure itself velocity.
What is it? Do you want to get some suggestions, new suggestions?
Yes. What would be the method? How could they measure it?
You don't have any idea. You don't have any enough knowledge.
Okay, then
Or do you want to make a debate out of
Well,
this method?
not a debate.
Can
I
you
was
target-
thinking about the very common, very easy ones, not too hard, very short ideas, not details. And just
continuous images.
the one for you, but in the water, underwater, the image is very not to be detected, so it is used if for recent research they use the LED marker or make the UV moves to the surface of the water to get the information about the image.
Okay, I think that this kind of device must be controlled by someone, or someone into a boat, so it can emit a sound and then calculate the difference between the waves, the sound wave that it emits and the wave sound that you receive, and then can calculate knowing the difference by the two waves, they can calculate the velocity.
Okay. You mean the wave?
The sound wave.
Sound wave,
yeah.
Under the sea.
Yeah, but it's like the same principle of sonar.
Yes. Okay.
You can think about how the airplane can detect the velocity.
I think he told us that the same principle is the airplane detecting.
Maybe not making sound. But anyway, they use GPS.
Yes.
Underwater you can't use GPS. You can use maps. And it's safe in your UV, and you can also use the Earth magnet field to navigate. So when you combine these two methods, it can control itself and navigate itself.
Yes.
And you can measure the velocity by measuring the resistance you receive. So the higher the speed, the higher the resistance, and of course you can know how fast the vehicle is.
Okay. As you told the disavailability of the GPS, so that for the UAV, it is the GPS is very good tool for the navigating. So if they need the very detailed logging, if they need that, they move to the surface of the water and get the information about the GPS. So yes, they cannot use in the ordinary cases with the GPS and other things you told about.
What's the resistance to measure the velocity?
Resistance?
So the water resistance.
Water resistance. Okay. So, like similar to one, the one way to measure the velocity is attach the device that is rotated by the water, so that check the RPM of the device, and they can also detect the velocity of the UV, not just the UV, but on the water vehicle. Okay, then I have one more topic, so can I move on to the next topic? I found some solutions that is already used to check the velocity. The 1 to 4 one is very old one, like the observation of floating log. That's the reason why the method of detecting the velocity's name is logger, aka logger. So first one is observation of floating some material, and second one is for the log chip name is log chip, and log chip is connected to the log line. So just throw them, and how long the log line get out of the vehicle per certain period of time. And third one is teaching the rotating device I told you for previous time. So, and first one is measuring the voltage. Make the impeller that is with the circuit of the developing the electricity, so that measuring the voltage of the impeller's voltage. So yes, the one. And fifth one is the using the pitot tube, so that they can use measure the flow velocity. And sixth one is that is very not ordinary one, but is to use the GPS. They go up to the surface of the water. And seventh one is EM log, that is electric log, is to put on the water, and because of the since the seawater is an electrolyte, so moving the seawater makes the difference in the voltage. And eighth one is the very most popular one, the Dockelaar log I told you first time. So second discussion is I want to what kind of mission would be done by the robot which is driving in ocean or underwater. So I bring some yes, just very for some examples. First one is the aquarium cleaning robot, and second one is that is very special one. I think they are this robot is made because to make the discovery bring the cultural asset in underwater, like the broken boat a long time ago. And it is also used for the seawall detection. Yes, and third one is that the robot's name is Jeros, and it is developed in the KAIST civil engineering that to make to get rid of the poisonous jellyfish on the under the water. Yes. Like this. There's very no line that to restrict the topic, the mission. Just tell me as you in comfort of you.
I think there's many fields like if we glad to use robots. The first example that comes to my mind is maybe like welding huge pipes underwater. And I know that like for example for ocean rigs or like any petrol industry, they use huge rig in the water. And nowadays they send welding experts, divers, just go in the depths and just weld. But this is a really risky and really like high skill requirement.
job. So I guess they almost done the robot station, but I don't know if nowadays we'll use it or not.
Okay.
But yeah, it could be a great application for a robotic system to weld things in the water, to repair those kind of huge pipes, circulating being in the water.
Use the robot to manage the height,
maintain the pipe or to implement it.
Okay. This is the mission. Okay. Yes. Thank you.
For fishing, make sure that the fish you want is catched, and not like the fish you don't want.
You mean detecting the fish cloud?
Yeah, I think nowadays there's a lot of bycatch or something. I don't know how to call that, but that you are fishing for tuna and that you get sharks and turtles and whatever fish you don't want. That it detects the unwanted fish. That's it free.
Okay.
One way or another.
Then you mean the assistant for the fishing?
Yeah.
Mm-hmm.
Something like that.
Okay.
Something to clean the ocean.
Something for the ocean. Okay. I didn't bring the image, but it is the one way to use the robot in the ocean. The shape of the trash can, someone made it. Yes. I think this is good too.
One issue could be the exploration, because a large amount of the ocean is unexplored so far. Maybe we can increase the knowledge about the ocean using robots.
Underwater exploration.
A bit similar to what Sebastian said. For offshore fish farms, sometimes there will be holes in the net or the container
Yes.
contains the fish. And fish will escape, and those fish are not like the fish that naturally lives in the ocean. They can actually pose a risk to the natural ecosystem, the ocean. So that's why it's important to prevent this. And these undersea robots could actually fix the net for the container.
Okay. The fish farm to manage the fish farm.
Right.
I think that's very innovative thing. Very efficient. In my case, I thought about the animal-shaped robot that which can find out records the animal's pattern, movement patterns like that. Yes, I think done. Thank you for attending the discussion.